Record. Okay. So again, we're looking at the top of page 3, example 2 of the notes. The answer A and B are what you see below, 0 and 2. So again, if you take the limit as x approaches 0 of absolute of x, as going from the left or from the right, they're approaching the same thing. Likewise, as x approaching -2 from the left or from the right, they're both getting closer to 2. So there you go. Now, C, D, and E are going to be a little interesting. As I'm approaching 0 from the left, so this is my left-hand limit. That's going to be -1. Because as I'm getting closer and closer to 0 from the left side, y is consistently -1. From the right side, my right-hand limit, that's going to equal +1. Because the LHL does not equal the RHL, we can say with confidence that for D, as x approaches 0 straight up, it does not exist. We do not have them linking up there. If I pick a random x value, like x approaching 3, it's just 1, because that's what we see there. You know, sometimes you can just look at just the y value because that's what's happening. So hopefully that went okay for you guys. The one thing that was interesting was at x is approaching 0, right? From the left side was -1, from the right side was +1. Therefore, those x approaches 0 does not exist. But everywhere else it existed for anything else we chose for either graph. So hopefully we're okay with that. All right, let's keep moving. So right now it is 9:52, so we've got about 18 more minutes. So let's talk about some of the analytical stuff that's going on here. So we've been finding limits using graphs or tables, graphical numerically, obviously. But these methods don't conclusively prove we have the limit. So you need to be comfortable doing these algebraic, which is what we're going to talk about. But we need some basic properties first. So using a graph, find the limit as x approaching -3 of fx equals 4. Well, f of x equals 4 is like saying y equals 4. You know, we should be comfortable drawing that, right, by now. So, of course, as x approaching -3, if you're going from, you know, here's like -1, -2, -3, -4, as going this direction and going that direction, you know, if I'm going to -3 from the left, -3 from the right, you know, it's still going to equal 4, right? So my left-hand limit is equal 4. My right-hand limit is going to equal 4. So, yeah, the answer is just 4. There you go. Now, let's say we use a calculator or a graph, doesn't matter, for this function, y equals x. So I'll shine a little spotlight. So x is approaching -3. Of course, the y value there is -3. If you were to do like, you know, a little table, let's say plug in -2.9, -2.99. So I'm coming out from the right side, or if I'm coming out from the left side, -3.1, -3.01. Yeah, you get -2.9, -2.99, -3.1. You know, I mean, obviously y equals x, right? So the bottom line is that y gets close to -3 as x approaches -3 from either side. I mean, these should be hopefully pretty obvious. The graph and just numerically kind of makes sense. So algebraically, or a property we can think of, is that if y equals a constant, your limit is just going to be the value of the constant itself. That's all. So here y equals a constant. The limit is that constant. We can assume that now. Here, if x is approaching c of x, then it just equals whatever x is, or in this case, c. So basically, whatever x approaches, whatever x approaches, y approaches is the same number. So for y equals x, and I'll get to your question in the chat in just a sec. For y equals x, whatever x approaches, y approaches, let me just move that, the same number. So we have a chat. Are there any exceptions to algebraic properties? No, for these, no. There are no exceptions. I mean, for other limits, yes, there will be other properties, but for these, no. No exceptions. Yeah, so that's what, so for example, if I ask you to find the limit of x approaches a random number like 1.28 of 5, the answer is still going to be 5. Or let's say I ask you to find the limit as x approaches negative root 5 of x, the answer is going to be negative root 5. So yeah, no exceptions at all. Yeah, and so here we just assume these to be true. So let's talk about some of these limit theorems. Let's actually apply some of these. Yeah, I think if I get to the bottom of page 4, that should be sufficient. And we'll just have to just do more of this on Thursday. But a homework will probably be textbook stuff. I don't think I'm going to do the worksheets. So I think the worksheets, we're not ready for it yet. I think we'll save the worksheets for Thursday. So Thursday we'll definitely wrap up 2.1. And I'll have to do a video on 2.2, obviously, over the following weekend. So we get back on track. Anyway, so we got about 10 minutes left. So some properties here. So if you're adding two functions, so let's say the limit of f of x as x approaches c, we call that capital L. Let's say for a different function, g of x, again, x is still approaching the same number as for the other one, c, but let's say that value of that limit's a much different number. Let's say it's m. So being hypothetical, we could say, let's say f of x is like 2, and let's say g of x is x. Then of course this would be 2 plus x, right? Which I know you guys can graph. Or this would be 2 minus x, which I know you guys can graph. Or this would be 2 times x, so y equals 2x, which I know you guys can graph. Or a random constant, like say 10 times 2, which would be 20. Or f of x over g of x, 2 over x. Or 2 raised to some power. Regardless of what your functions are, as long as you're adding two different functions, the limits can be added also. You could just say L plus M is going to be the value of the limit there. Or L minus M in this case. Or L times M in this case. Or the constant times your limit in this case. Or L over M in this case, provided that M does not equal 0, because that would be undefined. Or L raised to R over S power, whatever R and S are. So these should be pretty intuitive, hopefully. If you got two different functions and they have their own limits, and you're adding those two functions together, you want to find the limit of that addition, add the limits. Or if you're combining two functions by subtraction, subtract the limits from their individual values, using their individual values, sorry. Or if you're multiplying two functions, you want to find the limit of the product of those two functions, whatever those limits were individually, multiply them. So all those things should be hopefully intuitive using those limit theorems. And there'll be some textbook problems all assigned for that. That will just, you practice that. So it should be, again, homework should be pretty straightforward. Let's utilize this right now. And actually, to be honest with you, this is a pretty easy problem, example 5. But I'm going to use limit properties to kind of, you know, help you out. So let's break this off. Let's say I'm find the limit as x approaches 5 of 3x minus the limit as x approaches 5 of 13. And let's ignore the exponent for now. So this would be the same thing as the limit as x approaches 5 of 3x minus 13. So you could think of 3x as being one function, negative 13 is another function. You're subtracting those two. Well, I know that this could be broken down even further. 3 times the limit as x approaches 5 of 3. Sorry, as x approaches 5 of x minus, again, the limit as x approaches 5 of 13. So even the 3x, I could break down even more, right? The 3 is a constant, like we saw in property 4 here. The 3 is a constant. I can pull that constant off to the left. So that's just going to be, sorry, that's a 13. That's really ugly. So that's just 3 times 5. And that's just going to be 5 straight up. Because remember, this is a constant. And here, that's x. So x is approaching 5, so the limit was 5, but you have 3 times 5. And that's minus, oh, sorry, minus 13. Yikes. My bad. That was minus 13. So that's just 15 minus 13, which is just 2. And then you're cubing it. I mean, we did have the cube, right? So now when you do the limit as x approaches 5 of 3x minus 13 cubed, that's just going to be the value of my limit of 3x minus 13, which is 2 cubed. So that's using this property right here, which is just 8. So I know it's a little long-winded, but what I did was, if I broke apart 3x minus 13 cubed as limit of 3x, limit of 13, subtract those two. Limit of 3x was 15, limit of 13 was 13, subtract them, cube it. To be honest with you, you could just substitute. That's also fine too. As an alternate, which we are working our way towards that. Usually as your first thing you want to do is just substitute as an alternate method to what I just did, which actually is more efficient. Just plug 5 in. 3 times 5 is 15, minus 13 is 2, 2 cubes 8. If you have that luxury, most of the problems we'll do in this class, we won't have that luxury because I want you guys to think hard. I want you guys to do some algebra, which we're going to talk about on Thursday. We're going to talk about some more complex limits. We're going to definitely step this up on Thursday. But for now, yeah, just plug it in. Yes, you can break it apart using the limits I just did. You look at 3x minus 13, take the limit of 3x, take the limit of 13, subtract them. And the 3 can be pulled off to the left using it because it's a constant. 3 times 5 minus 13. 15 minus 13 is 2. And then you're doing the limit of 3x minus 13 cubed. You already know the limit of 3x minus 13 was 2. Using this property 6 here, 2 cubed is 8. So that's how I guess you would show the work. But to be honest with you, if you just substitute, I think we're fine with that. Yeah, graphically, absolutely. If you were to graph it, go to Desmos. I would probably just recommend that for now. You could graph in your TI calculator, but if you're to graph that, it's just going to look, I think something kind of like this. So I think this is at 13/3. That's my x-intercept. At 5 is going to be somewhere over here. And the y value is 8. So just getting closer to 8. That's all. So no need to really overcomplicate that one. So that's kind of the point I'm trying to make for what's going to happen for example 6. If you have a polynomial function, which we did, that's a polynomial, and sees some real number that x is approaching, then it's just f of c. Just substitute. So those properties, no one really uses them. I mean, you don't really show it. It's kind of mundane, to be honest with you. Just plug it in. So like here, just plug in c. C to the 4 minus 3c cubed plus 2 over c squared plus 1, call it a day. That's all you're doing. If you can't. I am going to give you problems where you can't. Where when you plug in whatever x is approaching, you're going to be divided by 0, or you're going to have something really weird, and then you have to do some algebra. We're doing that stuff on Thursday. We're doing the weird, the tough stuff on Thursday, because that's what we do. So, but yeah, just substitute. That's all. It's pretty easy. And we're getting close to wrap up, which is good. This is kind of a good place to stop soon. So we did incorporate a little more theory, just so you know, like talking about LHL and RHL and kind of exploring graphical numerical a bit more. We did talk about power, power functions a bit more. We did talk about some properties. Let me go ahead and clear this. You have a question? Yes, you'll when you can't substitute, you'll learn that on Thursday. On Thursday, you'll learn that. I'm not going to give you any problems like that for tonight or tomorrow, whenever you guys do your homework. Just one more thing. If you have like a fraction, find f of c over g of c. As long as f and g are polynomials. Obviously, we have like radicals and other weird stuff. We'll explore that also. But keep in mind that g of c cannot equal 0, right? Because then that would be an issue. In that case, then we'll talk about approach that on Thursday. This right here, we'll talk about on Thursday when that happens. So the question who just posted out in the chat, what do you do when you can't? We'll have that discussion on Thursday. But for now, we just can substitute straight up. So we're going to look at page 5 of the notes on Thursday. The homework should be pretty straightforward, and we should be able to kind of go through homework review a little more quickly. But 10 is going to be one of those weird ones, like you plug in 0, divide by 0. 11 is going to be one of those weird ones. 12 is a piecewise function. We have some trig stuff that are going to be a little weird. And then we're going to have some worksheets of work on that. So definitely we'll wrap up 2.1. Yeah, we're not doing a test at the end of next week. That's ridiculous. But what most likely will happen is we'll do 2.2 as a video over next weekend. We'll probably do 2.3 and then probably tie in 2.4. So I'm probably going to do the test by about a week. So I'm going to make sure I go to Schoology and update that. So you guys, well, actually, I haven't even put in Schoology yet. So there we go. So the syllabus is going to be changed, obviously, because, you got to be flexible. All right, I think we're all done for today. That's 75 minutes. You guys have a 15-minute break before B period, if you have a B period. If you want to stick around, I'll be around here because I do teach all day today, so I'm not going anywhere. I probably have to get up and stretch because I don't want to sit in the chair for 6 hours. So let me stop sharing, stop recording.